The final theorem I want to cover has to do with the number of edges on a tree. So if we let T be a tree with at least one vertex, then T has to have n minus 1 edges. Every tree has one less edge than vertex, or than vertex. Always. As long as it's a tree, as long as it's connected and acyclic, every graph that's a tree has n minus 1 edges. We want to prove that fact. Now, before I prove it, I want to show you that there is a technique for proving things about graphs, typically used for proving things about trees, but actually can be expanded to other types of graphs. It's called leaf deletion, which is a variation on induction. So I'm going to prove this theorem using this leaf deletion template. The way that it works is you use your initial step or basis case like you do in induction. What you do is you show that it has to be true, some claim has to be true for trees with n equals 1 vertex or vertices. It's singular, so I should say vertex there. In the induction step is to assume that it's true for all trees with n equals k vertices. Then let T be a tree with n equals k plus 1 vertices, and let V be a leaf on that tree. By the previous theorem, we know that every tree has a leaf. Then we let T prime be the tree we get by deleting that one leaf, T minus V. Which means that T prime has k vertices, and we assumed that because it's true for n equals k vertices, then it's going to be true for T prime. So we use the fact that the claim is true for T prime to somehow show that it's true for the original T with k plus 1 vertices. If we can do that, which is usually the tricky step, but if we can do that, then we will have proved that it's true for all trees. So let's come back to theorem 50.9 and do a proof by leaf deletion. Again, we're trying to prove that every tree has n minus 1 edges. So first of all, the basis step. Let T be a tree with n equal 1 vertex. So if it has one vertex, how many edges does it have? We know that trees with only one vertex, actually any graph with one vertex, can have no edges. And n minus 1 is 0, right? Because 1 minus 1 is 0, no edges. The formula works for trees with one vertex. So now let's do the induction step, or the hypothesis step, the induction hypothesis. We're going to assume that this statement is true for all trees with n equal k vertices. So up to k vertices, the number of edges would be k minus 1. Okay? So let's let T be a tree with n equals k plus 1 vertices, and let V be a leaf on the tree T. We're going to set T prime equal to T minus V, which means that T prime is a tree with k vertices, so T prime has exactly k minus 1 edges according to the hypothesis here. We assumed that if the tree size was k, that this formula up here held, so it's 1 less than the number of vertices, which is k minus 1. Remember, this symbol means the size of the edge set of T minus V, or in this case T prime, just T minus V. So we need to use that fact to show that that's true for T. Since V is a leaf, it means its degree is 1. There is exactly one edge that contains the vertex V. So T minus V deletes exactly one edge from the graph T, or the tree T, which means that T then has k minus 1 plus 1 edges, or k edges. That k comes from this assumption up here, or actually this k is what we're trying to prove, right? If this is n, then n minus 1 would be k plus 1 minus 1, or k. I've proved what I needed to prove, that this formula holds now for a tree with k plus 1 vertices. So I proved my induction step. Therefore, all trees with n vertices have n minus 1 edges proved. Interesting fact. I mean, you can go back and take a look at some of our previous slides. In fact, I'm going to jump ahead and show you. If you look at this picture right here, this is a tree. There are 1, 2, 3, 4, 5, 6, 7 vertices. There are exactly 6 edges. 1, 2, 3, 4, 5, 6. Guaranteed. This tree down here, in fact, both of these were trees. This path and this had 4 vertices, and notice there were exactly 3 paths. Exactly 3 paths. Every tree has n minus 1 vertices. All right, I'm going to back up right there. So this is where we were. Last thing I want to show you is a theorem that I'm not going to prove, but shows you an interesting connection. Not only does every tree have n minus 1 edges, any connected graph with n minus 1 edges has to be a tree. So theorem, if G is connected, meaning it has only one component, there is a path from every vertex to every other vertex. Not an adjacency, but a path. And it has at least one vertex. Then G is a tree if and only if G has exactly n minus 1 edges. So the theorem goes both ways. If it has n minus 1 edges, it's a tree, assuming it's connected. And if it's a tree, it has n minus 1 edges. And the proof for that is omitted, and that is all that I want to cover from Section 50. You are now prepared to do the homework for Section 50.